Hello, welcome to the NPTEL online certification course on deep learning. For last few lectures, we are talking about some of the popular convolutional neural network models, and in the last class we have talked about a particular model which tries to deal with a very challenging problem faced in the deep neural network, which is the vanishing gradient problem. So, the problem that we have talked about, that is the vanishing gradient problem, we have seen the architecture of a network known as GoogleNet, and we have seen how GoogleNet tries to alleviate the problem of vanishing gradient. In today's lecture, we will talk about another network architecture which is known as residual network or ResNet, and we will also see that how in case of residual network the vanishing gradient problem is addressed. And after that, we will also talk about another challenge which is faced in the deep neural network, that is how to choose the parameters or the step size when you update the network parameters or the network weights. So, today we will particularly talk about one particular approach to solve such a problem, which is known as momentum optimizer. So, let us see just briefly what we have done in the previous lecture. So, the problem that we tried to address is the vanishing or exploding gradient problem, and a particular network architecture we discussed is GoogleNet, and we have seen how this vanishing gradient problem is addressed in Google network. So, in GoogleNet, the architecture is something like this. So, as we have discussed in the previous class, the GoogleNet consists of 9 inception modules, and every inception module computes the features at different scales, starting with the convolution kernels of size 1 by 1 to convolution kernels of size 5 by 5. So, all these different features at different scales are computed by inception module in GoogleNet simultaneously, and the outputs of each of these feature extractor modules or outputs of each of these convolution kernels, they are stacked one after another to give you the feature map from a particular inception module, and then this feature map is passed on to the next inception module as an input for processing. So, these are the basic elements of the GoogleNet. And the way the GoogleNet addresses or tries to solve the problem of vanishing gradient is by making use of some auxiliary classifiers. So, as we have discussed in the previous class, we have one classifier over here which is actually the main classifier, and we have two more classifiers over here which are auxiliary classifiers. These auxiliary classifiers take the outputs from the inception modules which are in the middle of the GoogleNet and exploits the power of the features or the discriminative power of the features which are computed by the inception modules in the middle. And because these are also classifiers, so they also produce some loss function. So, both these auxiliary classifiers at this level and this level, they also compute some loss function. So, when you compute the final loss function, these two loss functions after scaling by a factor of 3 is added to the final loss function which is computed over here. And this entire loss function is used for back propagation learning, that is the gradient of loss function with the parameters with respect to the parameters are passed in the backward direction for parameter updation. So, as you are computing the loss functions in the middle of the GoogleNet, so the problem of vanishing gradient is believed to be addressed by using these auxiliary classifiers which are in the middle of GoogleNets. So, with this brief introduction of what we have done in the previous class. Now, let us try to see the other network that we are going to discuss today is the residual network or ResNet, and let us see that how this ResNet also addresses the problem of vanishing gradient. So, the core idea in the ResNet is it introduces skip connection or identity shortcut. So, the purpose of this skip connection or identity shortcut is that it skips one or more parameter layers or weight layers and feeds the input directly by passing say one or more layers to a layer ahead. So, the connection that is given over here, that suppose I have this is the output from one layer, and following this I have two more layers, say one layer over here and another layer over here. So, this activation from the previous layer is directly moved to two layers ahead and added over here to be passed on to the next layers. And this is done in addition to the regular path of the information flow in the forward path, which flows to these two weight layers as well. So, this skip connection is the core contribution or the core idea in the skip connection or ResNet network. And it is believed that stacking of the layers, this should not degrade the performance when you compare the performance with respect to its shallow counterpart, because we have discussed in the previous class that in many cases it has been found experimentally that the performance of the deep neural network, which is believed to give better performance compared to the shallow network for the same job, but which is not always true, and this happens because of the vanishing gradient problem. So, because of this skip connection, as these skip connections are introduced, so now it is expected that stacking of layers, or as we have more number of layers in our deep neural network, the performance should not be worse than its shallow counterpart. And while doing so, why it is ResNet? If you look at these two layers over here, what these layers learn? If I assume that output over here is my hx, so hx is nothing but x, but plus fx, where fx is the activations which are implemented these two layers which are skipped. So, hx will be basically fx plus x. So, what is fx in this case? Fx has to be hx minus x. So, this is the residual, and that is what is learnt by the layers which are actually skipped, and that is the reason this is what is known as skip connection or residual network. So, given that, so as we have already said that by stacking these identity mappings or giving these skip connections, the resulting classifier or the resulting network that we have, that should not perform worse than its shallow counterpart, or it should give at least the same performance as its shallow counterpart. And as a result, it is also expected that such deep networks should not give higher training rate compared to the shallow network. And during learning, when we have to pass the gradient or the error gradient from the output side towards the beginning of the network, such gradients can also flow from any layer to any layer before through the shortcut connections. So, from any layer to any of the earlier networks, any layer in the any earlier layer in the networks from which we had the shortcut connection or we had the skip connection, the gradient can directly flow to that connection as well. So, as seen over here, so whatever gradient is available at this particular level, so whatever gradient is available at this particular level, this gradient can directly flow to the layer beyond this. So, that is the advantage of the ResNet or skip connection. that the gradient need not flow through each and every layer in your deep neural network, and that is how it can avoid the problem of vanishing gradient. So now, given this, let us see that how the information flows through this residual neural network. So this diagram shows a 34-layer ResNet. So here you find that all these bypass connections, which are shown by the curved arrows, so they represent all the skip connections, which skips a number of layers in between to feed the information layers ahead. So the way this ResNet forwards the information, or as the information flows in the forward direction, is given by this. If I assume that this layer is at layer L, the previous layer is at layer L minus 1, and the layer previous to that is layer L minus 2. Then the information, forward information, which is available to the input of layer L, is basically a function of the activation at layer L plus 1, activation at the output of layer L minus 1, plus the activation at the output of layer L minus 2. And that is what this skip connection gives. This activation and this activation, they are added together, and that gives the input to layer Z, layer L. And the output of layer L will be a nonlinear function of this total input. So if I assume that the input to layer L minus 1 is A L minus 1, which is basically the output of the activation of layer L minus 1 is A L minus 1, and the activation output of layer L minus 2 is A L minus 2, and the connection weights from layer L minus 1 to layer L is given by W L minus 1 L, and the connection weights from layer L minus 2 to layer L is given by W L minus 2 L. In that case, the activation at the output of layer L, which is A L, is given by a nonlinear function of W L minus 1 L times A L minus 1, where A L minus 1 is the output or the output activation of layer L minus 1, plus B L. B L is assumed to be the bias at the input of layer L, plus W L minus 2 L times A L minus 2, where A L minus 2 is the activation at the output of layer L minus 2. And that can be written as it's a nonlinear function of Z L plus W L minus 2 L A L minus 2, where Z L is nothing but this term, which is the activation at the output of layer L minus 1. So this is what is Z L. So I can compute the activation at the output of layer L as a function of Z L plus A L minus 1 in case A L minus 1 and Z L, A L minus 2 and Z L, they are of same dimension. But if A L minus 2 and Z L, they are of different dimension, then I have to have a mapping by making use of a weight matrix, which is W L minus 2 L. So if there is identity, in that case I have Z L plus A L minus 2, that passes through the nonlinear activation of layer L, and that gives me the final output A L. And this is how the information flows in the forward direction through a residual network. So now let us see that how does this residual network perform the back propagation learning, or how these skip connections help to alleviate the problem of vanishing gradient. So while back propagation, I can have the gradient to propagate backward from layer L to layer L minus 1 following the usual link, this gradient can also flow from layer L to layer L minus 2 following the skip connection. So, the back propagation, I have two gradients. One is the update of the weights of WL minus 1, that is the update over here, that is given by delta WL minus 1L, which is minus AL minus 1 times delta L, and that is what flows through the normal path. And when you use the skip path, that is for updating these weights WL minus 2L, the gradient flow becomes delta WL minus 2L is minus AL minus 2, as AL minus 2 is the output activation of layer L minus 2 times delta L. So, this is what follows the skip path. And of course, if the skip path has got fixed weight, in that case this weight updation of the skip path is not required anymore, because in that case it becomes an identity matrix. And what is delta L? Delta L is the propagated error gradient at layer L. So, delta L is over here, right. So, you find that when this back propagation has to be carried out further, at this location you have the error propagation from both paths. One is the normal path, the usual path, and other one is through the skip paths. And it is skip path which helps in avoiding the problem of vanishing gradient, because from the previous layers the error gradient, the gradient is directly passed to the other layers in the forward direction, in the backward direction. So, this is how the vanishing gradient problem can be tackled using this residual network or ResNet. So, given this, as we have discussed about two different architectures, one is the GoogleNet and other one is the ResNet, and we have seen that how in these two architectures the vanishing gradient problem has been addressed. In case of GoogleNet, the vanishing gradient problem has been addressed using the auxiliary classifiers, whereas in case of ResNet, the vanishing gradient problem has been addressed by using the skip connections or the residual network part. Okay. Now, given this, now let us talk about the other problem, the other challenge that you face in deep neural network, that is during learning or during training of the network, how do you choose the appropriate learning rate, or how do you choose that what should be the weight upgradation step size? That is what is your learning rate. So, let us see how these problems can be tackled in or what are the different algorithms available for tackling this particular problem. So, what we will discuss today is one of the optimization approaches for optimizing gradient descent problem, optimizing the gradient descent operation, and the algorithm that we will talk about is what is known as momentum optimizer. So, let us see what that momentum optimizer is. Now, before that, let us see that what are the challenges in the gradient descent problem. So, in gradient descent problem, as we have said, the first challenge, the important challenge is the choice of proper learning rate or weight updation steps. If we choose the learning rate to be very small or weight updation steps to be very small, then your convergence or the learning rate is very slow, the convergence is very slow. At the same time, if the weight updation step is very large, then that may lead to oscillation around the minima of the loss function, or in some cases it may even diverge instead of converging. So, let us see how that can happen. For simplicity, I am assuming a loss function in one dimension. Say I have a loss function L, which is a function of a scalar parameter W, and I want to update the value of W in such a way that the loss value of the loss should be minimized. And this is what we have already discussed in one of our earlier lectures. So what I am going to do is just a sort of recapitulation. So to initialize, what you do is your initialization is done at random. Say for example, I have initialization somewhere over here. So W is chosen somewhere over here. So for updation, what you do is you take the gradient of L at this location and you update W in the direction of negative gradient. That means suppose this was my W0, and to have the W1, because the gradient direction is this, I take a step in the negative direction. So I come over W2 or W1, which is somewhere over here. That is my next estimate of W or the weight value. So here you find that as you are estimating the W over here, the value of the loss function that is reduced. Now the value of loss function is this. So my step of updation was this much. If this step size is very small, then I will slowly move towards the error minimum somewhere over here. So the number of iterations may be quite large if my updation step size is very small. If the updation step size is large, that is instead of W1 being here, suppose the W1 comes somewhere over here. If the updation step size is very large, and because of this, you find that your loss value straightway jumps from here to here, and in the process you are bypassing your minimum loss location. Of course, gradually you will come over here, but there will be an oscillation. It may so happen that if the step size is very large, in that case I may even go over here. It can go like this, and in such cases, instead of converging to the minimum loss location, you are actually diverging. So you find that choice of proper step or proper learning rate is very, very important. So this is one of the challenges of the gradient descent problem. The other challenge is that, okay, I can have a pre-schedule of learning rate. That is how the learning rate will change over the iterations. That can be scheduled beforehand. So that is what is pre-scheduling. But the problem in that case is that the same learning rate has to be applied to all the parameters, which might not be a wise choice, because our data may be sparse, and not only that, the different features may have different distributions or different frequencies. So if it is so, then updating all these parameters by the same extent or using the same step size may not be proper. So what I need to do is, depending upon the frequency, a larger update I can use for rarely occurring features, whereas for those features which are frequently occurring, I can have a smaller update size. So this is another problem in gradient descent optimization techniques. The other problem, which is also very, very challenging, is that my algorithm may be trapped in suboptimal local minima, particularly if the error surface has a saddle point, something as shown in this diagram, say as over here. So what are the saddle points? Saddle points are that surface, that point on the surface where in one dimension the slope rises, whereas in other dimension the slope goes down. So it is over here. In this direction the slope is rising, whereas in this direction the slope is falling. So this is what is saddle point. And the challenge comes because of the fact that these saddle points are usually surrounded by plateau of the same error, over which the gradient value is negligible. And when it is so, then the gradient descent algorithm or stochastic gradient descent algorithm find it very difficult to come out of this problem. So these are the different challenges that we can have in gradient descent. So now let us see that how we can tackle this problem. What I can do is, I can assume, say, this is the surface given by the loss function, and for simplicity I am assuming that my parameters are two-dimensional parameters, or the weights are two-dimensional weights having W1 and W2. And the way you start your gradient descent operation is that you assume that initially the parameters or the weights are, say, initialized somewhere over here. Say initialize the weights somewhere over here. And then what you do is you compute the gradient at this location, and the direction of gradient is such that it falls along the valley and finally it should come to the minimum location. So I can assume that I place a ball at this location with initial velocity 0, and that ball will have a potential energy which is given by U is equal to mgh. And the force which acts on this ball is, say, F, which is nothing but gradient of this potential energy with negative. So minus grad U is the force acting on this ball. And under the action of this force, the ball falls along the surface, and while falling on the surface, it gains the momentum. So while falling, it will drop down to, it is expected that it will drop down to this minimum point on this surface. Okay, the algorithm is fine if the surface is a well behaved surface or it has equal curvature in all the directions. But the problem arises if we find the surface is not well behaved, or the curvature in one dimension, in one direction, is more than the curvature in another direction. And that is where this momentum optimization technique, which is nothing but an approach for making your gradient descent more efficient. So these are the cases where the momentum optimization technique will help in faster convergence of the gradient descent algorithms. So let me stop here today. In our next class, we will talk about this momentum optimization. Thank you.